Hi everyone. In this video, we are going to do a brief review of polarity, which we talked about in intro chem. You saw it in advanced chem, but we're going to review it again. Okay, so when we talk about polarity, what we're really talking about is charge distribution within a molecule. And it turns out that charge distribution within a molecule plays a huge difference in the properties of the molecule, right? Molecules with uneven charge distribution are more likely to be water soluble. They're more likely to interact with different things, whereas molecules with even charge distribution don't dissolve in water. They interact with oil. Intermolecular forces are different. Interactions are different. So when we think about, so it turns out to be really kind of important to think about charge distribution when we're looking at molecules, when we're assessing for their properties. Charge distribution is key, right? So we're thinking about how atoms are connected, how atoms are arranged in three-dimensional space, and then looking at charge distribution across the molecule to help us kind of define some properties. And so when we think about this, there are two ways for us to think about charge distribution, and there are two things that affect charge distribution, one of which is formal charge. So looking at specific atoms that have gained or lost electrons, right? And that's where formal charge comes in. And then the other way is looking at it kind of inductively. So thinking about areas of the molecule that are electron rich and areas of the molecule that are electron poor due to unequal sharing. So this isn't that something has lost or gained electrons. It's just that the electrons are unequally shared. So let's take a look at formal charge first, because it tends to be a little bit easier to think about. When we think about formal charge, we're looking at individual atoms that have lost or gained electrons within our structure. And so we have molecules or regions of molecules that are fully positive or fully negatively charged. If we look at the structure down here, if we look at it, this is called an amino acid. You talked about these in biology, building blocks of proteins. At pH 7.4, this is the structure that exists. So if we look at this nitrogen over here, nitrogen is making 1, 2, 3, 4 bonds, which means that it has a +1 formal charge. And this oxygen over here is making 1, so it has a -1 formal charge. So overall, it's neutral, right? So overall, it doesn't have a charge. But if we look at this molecule itself, oh my God, uneven charge distribution, right? This side of the molecule is positively charged. This side is negatively charged. So this has a lot of uneven distribution. Which means this molecule is very polar, right? Polar molecules have uneven charge distribution. Nonpolar molecules have even charge distribution. And this is pretty much as uneven as it gets. You got regions of the molecule that are positively charged and regions that are negatively charged. Okay, so beyond that though, right? Sometimes molecules have uneven charge distribution when there's nothing there that's positively or negatively charged. And that happens through things that withdraw electrons or things that donate electrons within to the system. And so when we think about the polarity of a bonded molecule, we're looking at uneven charge distribution that's caused by the presence of what are called electron withdrawing or electron donating groups. This polarity creates partial charges, right? Partial regions of the molecule that are partially positive, partially negative. We're not adding or gaining electrons here. We're just changing the way that those electrons are distributed between bonds, within bonds, right? And this is determined by the electronegativity of the atom. And remember, we talked about this last year, and we said that electronegativity is the ability of an atom to attract bonding electrons to itself, right? So how hard is that atom or that nucleus pulling on those bonding electrons? Remember that electronegativity increases towards fluorine, and that those values are on the periodic table in class. When we think about the atoms that we care about, or the atoms that we care about in organic chemistry, we're going to come up with a list of something that's going to go hydrogen, carbon, nitrogen, oxygen, fluorine, and we got some halogens floating kind of in here, right? Chlorine and bromine are somewhere around in there. Actually, bromine's on the other side. We have periodic tables in class to see what those look like. And remember, this is kind of like tug of war. So when we look at that, the electronegativity different, what matters when we talk about electronegativity and bonding is the difference in electronegativity between the atoms that are present. So if we have no difference, or if we have a small difference in electronegativity, let's take a look at, for example, carbon and hydrogen. So carbon has an electronegativity difference of 2.5. Hydrogen is 2.1. Difference in electronegativity here is 0.4. That's considered a small difference in electronegativity. So when I look at the distribution of those bonding electrons, so I have bonding electrons here. Remember, that's 2 electrons. And I kind of plot where they are. Right? The electron density here is going to be pretty much right in the middle between the carbon and the hydrogen. It's going to be a little bit closer to the carbon, but not by much, not enough to really make a difference. So because those electrons are right in the middle, that electron distribution, that electron density is completely evenly distributed between carbon and hydrogen. So that bond is what we call non-polar, right? Where the electron densities are evenly distributed. For organic chemistry, we don't really deal with large differences in electronegativity. We deal with what are called medium differences in electronegativity. So this would be something like hydrogen and oxygen, right? So if I have a bond between hydrogen and oxygen, and I do the same thing again, remember that hydrogen has an electronegativity of 2.1, oxygen is 3.5. So in this case, the oxygen is pulling a lot harder on those electrons than the hydrogen is, like a tug of war, right? It's oxygen's kind of hogging the electrons. It's like when you watch TV with your little brother, right? You're sharing, but you get to decide what you're watching more often. You're hogging the remote. Oxygen's hogging the electrons. So if I were to plot electron density here, what I would get is a higher electron density towards oxygen and a lower electron density towards hydrogen. So that this oxygen is carrying a partial negative charge and this hydrogen is carrying a partial positive charge. Partial charges, right? They're partial charges. It's not a full charge. The electron hasn't fully been transferred, but oxygen is hogging the electrons more than the hydrogen is, right? Another way to represent this, remember, is that this creates what we call a dipole, which is an uneven distribution in charge. And so we represent that with that arrow vector, right? So if I have a difference in electronegativity that causes the electron density to be unevenly distributed, does that necessarily mean that the electron density within the entire molecule is unevenly distributed? Well, no, it actually isn't, right? Remember that it is possible to have polar bonds, what are like unevenly distributed electrons, in a non-polar molecule. There's another factor at play here, which is that the molecule, which is the symmetry or how those polar bonds are arranged in three-dimensional space. If the molecule is symmetrical in three-dimensional space, like let's look at, for example, carbon dioxide. So if we look at carbon dioxide, it looks like this, right? The carbon-oxygen bond is polar. Carbon is electronegativity is 2.5, oxygen is 3.5. That's a polar bond. I have dipoles here. But remember that this molecule, because of 2 electron domains, it's linear. Those dipoles are the exact same magnitude and they're pointing in opposite directions, which means that the dipoles cancel each other out. And if the dipoles cancel each other out, then the molecule is not polar. So overall, the charge is distributed like it's not a polar molecule, so that would not be considered polar. The oxygens do carry a partial negative charge, but because that partial negative charge is distributed and the partial positive charge is on the carbon, it's not a polar molecule. Okay? But if the molecule isn't symmetrical in 3 dimensions, like let's say that I have HCN, just to go with the same linear example, right? So for HCN, I have a tiny dipole between the carbon and the nitrogen, and I have a larger dipole, or between the carbon and the hydrogen, and I have a larger dipole between the carbon and the nitrogen. But if I look at this molecule, it's not symmetrical, right? Those dipoles actually don't cancel each other out. They add up to a larger, what we call molecular dipole, which means that this molecule is polar. When I add those dipoles, I get something. I get a net dipole. So there's a net dipole here, which means that that molecule is polar. Right, so about this. To determine whether or not a molecule is more polar or less polar, we're looking for 2 things, right? Does it have polar bonds, right? Polar bonds determined by the difference in electronegativity. We usually say that difference has to be 0.5 or greater. And then so it has to have polar bonds, and it has to be it can't be symmetrical. So if it has polar bonds and it's not symmetrical, it's a polar molecule. If it has polar bonds and is symmetrical, then it's a non-polar molecule. So this is all well and good, and we've seen this a lot with small molecules, and we'll do some practice with smaller, tiny molecules like the kind that we did in intro chem. But when we look at larger molecules, when we look at more organic structures, the larger structures that we're starting to deal with, oftentimes these molecules can have both polar and non-polar regions, so regions that are greasy and regions that will interact with water. The classic example of this is the phospholipid. And you heard about these in biology. Phospholipids make up your cell membranes. And so they work because this part of the molecule over here, looking at that structure, is only carbons and hydrogens. So because it's only carbons and hydrogens, it is not at all polar. Right? It's just not because of the carbon and hydrogen structure. But then if we look at this end of the molecule over here, right, this end of the molecule turns out to be actually pretty darn polar. And in fact, it's got a charge. Right, here we're looking at carbons and oxygens. So we have electron-rich oxygens. We have a negative charge on that phosphate group there. Depending on what that H is, it could even get more polar. But we have this region of uneven electron distribution. So this part of the molecule over here is polar. This part of the molecule is nonpolar, right? That property allows the membranes to form, right? Because remember that the cell membranes form so that this part, the tails, are kind of oriented together and the heads are oriented towards the water side, which allows for the formation of that bilayer, which allows membranes to do what they do. So quick recap, and we'll do some more practice in class. Right? Charge distribution plays an important role in determining the properties of the molecule. The distribution of charge is determined by adding or taking away electrons from atoms, so looking at formal charge, and unequal electron sharing, or polarity. Polar organic molecules, if I'm just looking at it, I see lots of oxygens, nitrogens, halogens tend to be more polar. Non-polar organic molecules contain mostly carbons and hydrogens. And remember that molecules can have both polar and non-polar regions. The larger one is compared to the other, molecules can be more polar or less polar, right? It's not a dividing line. It's not a hard and fast, oh my God, this molecule is polar and this molecule is not polar. It's like, it's a continuum, right? Things can be more polar or less polar, and things can be kind of partially polar, etc. All right, so if you have any questions, please make sure you bring them to class with you, and I'll see you next time.